Hey, everybody. I'm Francisco. I am here to talk about RAG and fine-tuning. I guess I can introduce myself. I said I'm Francisco. I'm a senior principal software engineer at Red Hat. I spent most of my career working at financial institutions and startups and technology companies, working on data and machine learning, applying that to build models for a lot of financial and risk problems. At somewhere along the way, I ended up becoming a maintainer for Feast, the open source feature store. I ended up working on the Kubeflow steering committee, and I stumbled into working at Red Hat for all things AI related. And I'm really, really excited to talk to you all about RAG and fine-tuning, an area that I'm particularly passionate about, which is a really weird thing to be passionate about. And Xiao, would you like to introduce yourself?
Yeah, sure. Hi, I'm Xiao Wang. I'm a member of Kubeflow and also a maintainer of Kubeflow Trainer, Archive and SDK. Besides, I'm also a graduate student in Shanghai Jiao Tong University. Yeah. The original speaker is Andrey, but he cannot talk due to some internal reasons in his organization. But we also want to thank his help to this talk. Yeah.
Yeah, thank you. Yeah, so any civil person has an agenda, and so I thought I'd list out what our agenda is for today. Like the first thing I want to talk about is why AI projects fail, because that's like a common thing. If you went back 10 years ago, people talked a lot about like why data science projects fail, and now there's a similar analog happening with like AI projects in the era of generative AI, where we ignored all of fine-tuning and just talk about inference. And obviously, a lot of enterprises are experiencing that. And like, well, there are obvious reasons why, and I'd like to talk about how you can help solve some of them. Not perfectly, because I'm not here to do marketing. Yeah. And so we'll talk about that, right? And then we'll talk about what's RAG. RAG is kind of like the cornerstone that people use to solve hallucinations. It doesn't quite solve it, but it helps to reduce some of it. We'll talk about the history of RAG, which I think is really neat. Why did RAG become so popular? Why fine-tuning models with RAG makes sense, and how I can fine-tune models for RAG, and using Feast and the Kubeflow Trainer. And then we'll do a little bit of a demo. I have things here that I have screenshots of. We have a link to repo. We're still doing some minor developments of it, but it's a good working proof of concept that lets you kind of show how to actually scale this out and really build it on your proprietary data. And then we'll have some time for Q&A. And so please feel free to ask lots of questions or insult me, whichever you'd like. So why do AI projects fail? I think people broadly just say hallucinations, and that's like a really vague, fuzzy thing. To say like, oh, well, this model just made it up, but like these models, just by virtue of what they do is make things up, right? By virtue of generative sampling, probabilistically from a distribution, like that's just what these models do. So hallucination is a feature, not a bug. I think Andrey Velichkevich famously said that, and that's just natural. But there are really two things that happen: either the model has memorized something via training, or you're doing what's called in-context learning, i.e. you put in some chunk or a prompt into the input of an LLM, and it's meant to say something about it. Usually people talk about this in the context of question answering, and then that's kind of what RAG has done. And people try to solve the hallucination issue with RAG, right? But in the old training world, we were very much focused on fine-tuning. We knew that fine-tuning or just training models, traditional models, helped you resolve a lot of your problems, right? And you were able to really quantify what was a hallucination or a misclassification or an error in the old predictive ML world, and then just run gradient descent on it. So it was very simple. You could just train your models on the things you got wrong, and you'd do better. But again, now we kind of broadly say, well, it just hallucinates, and kind of throw up our hands. But fine-tuning doesn't really work as well in the Gen AI era because it's super expensive, and people are just really apprehensive to do it because I don't know about you, but I don't fork over H100 money just willy-nilly without knowing whether or not something's going to work. even though I'm deeply passionate about this stuff. And so what people kind of did was say, well, we'll just throw in RAG and prompt engineer and see if it works. But really what I'll go on to show you throughout this talk is that you can actually do fine-tuning on RAG, on at least the retrieval aspect of it. And it's actually cheap, and it can work really well. You can scale it really well, and you can actually get a lot of performance gains from it. Cool. And so I kind of want to walk backwards a little bit. What is RAG in 2025? Now there's a lot of talk about agentic RAG. I won't really talk too much about that, but it's pretty much the same as RAG, but then you let an LLM basically decide when you do RAG, so it's somewhat similar. But RAG stands for Retrieval Augmented Generation. Retrieval means that you go and pull some data out of a database. People usually use vector similarity search, which means that you're doing a dot product between two embeddings. And embeddings are essentially a numerical representation in some vector space between two sentences. People call this chunks. And what people do by convention is they embed a query, which is like the thing that you put into ChatGPT, and all of the data that's in some vector database. And they use the cosine similarity to calculate the distance. It computes that for all of the chunks in the database that are within the set of data that you actually want to look up, and calculates a metric out of it. And then they, sort that distance metric, and then choose the closest set of chunks. And just again, by convention, they choose the top K, and K sometimes people set it to 3, sometimes people set it to 20. That's active area of research, or people tinker with it. And then they put those chunks into the prompt that you then feed into an LLM, and then it spits out something coherent, hopefully, that doesn't hallucinate. And this is kind of a very trivial example at the bottom, where, if you were asking, let's say Wikipedia, where is Barack Obama from, you would hope that the system would pull out born in Honolulu, Hawaii, right, from that chunk, if you did a good job, and the vector embedding had matched that pretty well. And again, there's a lot of advanced things people can do with hybrid retrieval and different ingestion strategies, and I won't really talk too much about that. But that's really the gimmick that people do in 2025. And I think it's really interesting, I think it's really fun, but it actually ignores history. And so, I really get excited about this part of the talk because the history of RAG is really fun. It was originally presented in NeurIPS back in 2020. By Meta AI Research, and the original paper, and this is a snippet from it, talked about the retriever aspect and the generator, and how you could end-to-end back propagate them. And what that means is that you're going to actually train, stochastic gradient descent on both this retriever, this BERT model, and this generator, which is the kind of traditional inference thing that we're doing, right? And it's really important to understand this, that RAG was originally about fine-tuning, and it really wasn't about inference at all. And that's because back in 2020, it was still, I think, just on the cusp of ChatGPT taking flight. And so people just weren't as familiar with LLMs. And it was like, oh, okay, cool. These people came up with this interesting technique, and nobody cares because people are just still kind of training in silo and research for fun. And but they actually showed a lot of performance benefits. And again, if you look at the paper, what they called the retriever and their vector similarity search was actually what they called it was maximum inner product search. The kind of dot product between a tensor and then choosing the argmax. For those of you that aren't familiar, fine tuning is basically taking a base model, maybe a llama 3.2 billion parameter model, and then fine-tuning it, like literally running stochastic gradient descent on that model with some set of data, usually your own, and that you get a new version of that model with a set of modified weights. The example there at the bottom is with a Qwen 3. And often this is called domain adaptation if you take it for like let's say, like financial domain, and you really want to tailor a model from being general purpose to one that's really specific to finance for whatever reason. And again, there are three key components to it: the query encoder, the retriever, and the generator. But why did RAG become popular? Why did we forget about fine-tuning? And it was OpenAI is actually the answer, which is really fun. The paper was published in late 2022. Again, ChatGPT took flight in October 2022. And Google Trends kind of shows that correlation. And the reason that I call this out is because in ChatGPT's early documentation for those that were really early users, they actually told you, like, oh, don't do fine-tuning, just do RAG. Even though that was kind of like an abuse of RAG as an acronym. But it is a really catchy acronym, right? So it sounds great. So I think it's more power to them, and I think it actually works so well in practice that it's super intuitive. And the other important part of it is that it was actually much cheaper than fine-tuning. As I mentioned kind of at the start, fine-tuning can be really expensive because of the barriers to entry with an H100. People have gotten a lot better at some of this, right, with LoRa and different low-rank adaptation strategies, but it's still a lot harder, right? Fine-tuning is not as easy as training a traditional model from like the Titanic Kaggle data set, which like you can do in 2 seconds on an iPhone. But we should explore that. And as models get smaller, it's inevitable that we will start to fine-tune models more and more. And in the RAG case, you can actually get a lot of performance gains by just, again, fine-tuning the retriever. And I took this quote from the paper. I'm not going to read it, but it's really great, and it really talks about the benefits of fine-tuning and really adapting memory for your specific domain problems. And it's kind of obvious to say, right? But I'll say it anyways, that retrieval is a critical piece of RAG. I think people kind of just mush them together. But in practice, I think most people end up choosing the best inference model always, pretty much. Whether it's GPT-5 or GPT-20 or Anthropic's Cloud or whatever, I don't know. People tend to choose their favorite one that's whatever's flashy this week, and then they kind of ignore the retrieval. But again, what goes in it is really, really critical. Like you could think about the pathological example of like, that Obama Wikipedia example where if I just randomly pulled out like Alaska, it might have accidentally said Alaska just because that's within the context. And it might be a coherent reason for it to say that, but that's not actually a very functional system. So to reduce it, bad retrieval equals bad generation, probably. Good retrieval means maybe good generation. You have a much better shot at it, not guaranteed, obviously, because these things are probabilistic in nature, but, odds are going to be increasing in your favor. And the more practical thing for enterprises, when you do this, when you fine-tune a model, you actually get your own specific model that's fine-tuned to your idiosyncratic jargon. And what I mean by that is like every enterprise or business or whatever has their own set of language about things, even acronyms. Acronyms are a great example where, I think like CRMs. CRMs mean like 3 different things to 8 different companies for whatever reason, right? Customer research management or something. And so it's important to be able to actually represent that intuitively into these models. And you can do this, again, through fine-tuning and RAG. And more importantly, again, you can decouple this problem. You can fine-tune the retriever very cost-effectively. And then you don't actually have to spend all the money on a big old H100. So how do you do retrieval fine-tuning? Why is it cheap to do? It's cheap to do because the number of weights are way smaller, about 141 times smaller. As an example, the Llama 3.2 billion parameter model, obviously 3.2 billion parameters versus like the mini LM sentence transformer model, which is about 22.7 million parameters. So that's a huge difference. And so you can actually, even if you did nothing other than fine-tune the embedding model, you're working on consumer hardware. You can do a small set of training on that alone without doing LoRa or QLoRa or anything else. And you can get a lot of performance gains. And people run these on CPUs. A lot of enterprises, obviously everyone's buying up GPUs, and I think that's great because the future is GPU-centric, probably. But that doesn't mean we have to throw away CPUs. I have them on my computers. I like to use them. I have a bunch of data that I like to hit with embeddings, and it can work just fine. And And again, you can get performance gains from using a GPU. That's without a doubt. But for all the existing infrastructure and for all of your existing AI problems, you can actually get by pretty far. It's a more pragmatic compromise than it is trying to flex anything. And you can scale your data the way you've scaled your ML models for the past like 20 plus years, right? The nice thing about models as small is that you can really hit it hard with a lot of data. And over the last 20 years of machine learning, people that were running like Spark MLlib, where people gained their competitive advantage was really on large-scale data training, right? And really, really harnessing those weights for your own specific domain, whether that be credit or recommender systems or whatever have you, right? In this case, sentence embeddings. And probably my favorite part is that this is the opportunity where you can really extend for more advanced information retrieval optimization methods. So I mentioned hybrid retrieval. You can actually make these models, these models reduced to a classification problem. In the example at the beginning with the Wikipedia chunk, it was, does this chunk belong in the context? And when you frame this as a classification problem, what you can then say is like, oh, can I enrich this particular chunk with a bunch of metadata so that I can actually maximize the performance of this classification problem, which we have been doing for, again, 20 years. And we really know how to do that well and serve that efficiently. And if you look at a lot of Google's early papers and recommender systems, it actually ends up being a very similar analog to how really advanced retrieval systems behave. And so I think it's a great opportunity for really cheap optimization, especially at scale. So how do we do it, right? Feast and the Kubeflow Trainer, via PyTorch. And so the simple thing that we can do is we can process training data with Feast and some compute engine. In some cases, people choose Spark. We just announced support for Ray. We have Dask, we have Pandas, whatever. And you can store that training data set that you process and embed in the Feast offline store. And then you can fine tune the retrieval model with the Kubeflow Trainer. And we'll talk a little about what that looks like in a second. And then at inference time, at serving time, you can actually serve those feature transformations or those embeddings with Feast. And you can scale this on Kubernetes, and you can serve this, and it'll do just fine. You can, again, accelerate it with GPUs, and I think that's great, but you can get by pretty far on CPUs. Yeah. And so now, natural question, what is Feast that I've been talking about besides eating at Thanksgiving? Feast is an open source feature store. What is a feature store? Feature store is a data and AI toolkit that helps teams scale and operate production AI and data systems at scale. And it's basically a declarative framework that plugs into a bunch of different offline stores or analytical data warehouses and online stores, production-ready databases, whether it's Dynamo, Redis, Milvus, Cassandra, you name it. We support it. And in the offline stores, we support Spark, streaming, Snowflake, BigQuery. We really like users to power it. I list some of the adopters and contributors there. We have some big names, and I've served this at scale in my past life for Black Friday checkout, and it worked great. And the reason this works great and it's such a good focus and such a good fit for RAG fine-tuning is because Feast treats serving and training as first-class citizens. And so the symmetry between them is really, really important, in part for model reproducibility and model lineage. There's a long laundry list of reasons I linked them here about some of the lessons that the Feast developers learned over the last 10 years of production machine learning about the headaches you encounter serving these data systems at scale. And so we try to design for them. Not perfectly, but we do a pretty good job, and it ends up helping a lot of teams. And so we have 17 million PyPy downloads, 6.2 thousand GitHub stars, and 317 contributors. And like I said, used by a bunch of different folks. I built custom versions of feature stores at a bunch of different financial institutions, and then eventually ended up saying, why don't I just settle on Feast? And so that's how I ended up doing this. What is the Kubeflow Trainer?
Please allow me to introduce Kubeflow Trainer to you. But before I begin, may I ask how many people have heard of Kubeflow and the Trainer? Please raise your hand. Oh, so many people. Oh. Kubeflow Trainer is a sub-project under the Kubeflow ecosystem, and it mainly allows users to scale the ML code on Kubernetes effortlessly. This enables data scientists to quickly iterate their ideas on model training and model fine-tuning. Starting from 2017, Kubeflow has accumulated over 200 million PyP downloads and over 33,000 GitHub stars and near 3,000 contributors. It's a joint effort that opens from the open source community that makes Kubeflow successful. Thank you. With regard to LLM fine-tuning, Kubeflow Trainer provides a streamlined workflow, as this graph shows. Data scientists will use the Python SDK to customize this workflow, and the trainer job will first download the model and the dataset from the remote, and then start the fine-tuning jobs, and finally export the model to the cloud storage after the fine-tuning job is ended. It's worth noticing that all these processes do not need individual involvement. It's all automatically. Not restricted to LLM fine-tuning, Kubeflow project also supports MPI-style training and elastic training. As for the LLM frameworks, it supports PyTorch, Hugging Face, DeepSpeed, MX, and we also plan to support JAX and XGBoost natively in the future.
Awesome. Yeah, and so, why do these things fit together? Kubeflow and Feast have had a close relationship for a long time. It was part of the reason that I was really excited to be on the Kubeflow steering committee. If you look a little bit on the internet, you'll see that I've written quite a bit about it. And the way that we think about this is the kind of AI lifecycle. You have AI practitioners, people that are, iterating on data, iterating on model hyperparameters. In the old world, the experimentation cycles used to be a lot faster. With larger scale models, there's a little bit more wait time, and so maybe they experiment a little bit less and have more coffee, who knows. But a lot of the old world was in feature generation. Now people call it prompt engineering or in-context learning, tinkering. But the analogs are still the same. You still have to work with this offline experimentation of data that you feed into some stateful representation that I call a feature store, Feast there. And all of these things fit together into this entire life cycle of how you actually manage AI production systems at scale, where you might want a model registry, you might want an inference endpoint that can actually support multiple models for different things, not just one. Then you have to kind of figure out, well, how do you serve this data from different systems when you have multiple microservices that you're pulling data from, and how you manage the SLAs with those, and the actual consistency guarantees of different data sources ends up becoming real production challenges with ultimately just trade-offs. And luckily, we've thought through some of these things and build out some solutions that connect the kind of different Kubeflow projects together. And so if you look at the Kubeflow documentation, you'll find a lot more information about it. Yeah. So now let's talk a little bit about how this stuff looks like together at a very high level, because we only have a few minutes here. So there's an example data set that I wanted to go over, and we used the Wikipedia data set, which is pretty standard, where the title of the Wikipedia table is the query. The text or the chunk is right there listed, and what we do is we have a small subsample and 660 observations chunked with embeddings, and so each chunk is embedded, which just gives it a list of numbers. In this case, I think it's actually like 384, and it turns out to be like 604 kilobytes of data, so not a ton, enough that you can run this on your laptop. But again, gives you a start to where you actually can scale this horizontally across pods, and that's what's really fun. And so the labels in this case end up being the positive samples, where in this query, where the text is actually like a positive sample for it. So if I make an input query and I get this text back, that's good, right? If I make this query and get another Wikipedia chunk, that's bad. And if I get something that's semantically similar to this chunk, but it's not this query, well, then that's really bad, and we call that a hard negative. And so that's kind of the basic intuition of this supervised machine learning problem. And so we take the existing embeddings, the mini LM sentence embeddings, and this training loop, that model.fit call that you see on line 172, yeah, 372, sorry. It gives a loss function. It specifies some data loading parameters and some sampling and an evaluation within that loop, and that's just a convention. Again, I list the base model there with 384 vector dimension, and the loss function, the contrastive loss, you can look it up, it's interesting. Here I chose 200 epochs for whatever reason, and 16 is the batch sample size, so that's how many actual records are actually being fed during one iteration of stochastic gradient descent. And so this is actually the Kubeflow Trainer code.
Yeah. After you define the training loop function, you can pass the fine-tuning functions, hybrid embedding training, and parameters like epochs, learning rates, and batch size to this SDK. Also, you can specify the number of parallelized training nodes and allocate the CPU and memory resources to it. After setting all of these configurations, you can run the command and start the fine-tuning process. The Kubeflow Trainer will create a workflow without individual involvement to fine-tune the models for you.
Awesome. And it's not a lot of code, so you have to have someone with the Kubernetes background help you deploy this, but then your ML engineers or your AI researchers can really go ham on training on Kubernetes. And so the results, it works, is kind of the answer on this small subsample problem. And what it does is this contrastive loss pulls, again, chunks that are not meant to be close together, pulls them away, right? And it, this loss function kind of outlines it how. And it separates chunks that are hard negatives from positives, the truth. And serving the fine-tuning embedding. So that's where Feast ends up playing a big valuable part, where this declarative code, assuming you've deployed Feast, is what actually you can do to serve the production model. You can add a small function that does the sentence embedding with the tokenization. You can put this in a container. You can load the model at build time, so that way you're efficiently running it. And it'll work. It'll work just fine. And then you can have this all declarative in your API and use GitOps with it. And these embeddings basically become a feature view or a feature. That's the enablement. There's other metadata here and ends up being used to actually update your database, and it stores a key value, but that's all just kind of stuff. We have an operator, and you can deploy it with Helm. You can just deploy on a pod, however you'd like. And then serving the fine-tuning model, this is, what an architecture could look like for your AI platform that serves data. And there's a whole bunch of stuff here. I won't read through it. I will just mention it, and we can talk about the slides later. I'm happy to answer questions about it. This is also on the Feast documentation. But the idea is that Feast helps pull, this online database, this offline data analytics warehouse, and this idea of giving a client to your end users to be able to interact with that helps give everyone a common language. And so Feast in our future work, first-class support with the Kubeflow SDK. That's what we're going to start working on pretty soon. We just added support for Ray and KubeRay. We just joined the PyTorch ecosystem. We're doing more transformation support. Image and vector retrieval we support. We've had a long history supporting recommendation engines. We have a great UI with a data and feature catalog. And Kubeflow Trainer. Kubeflow also joined the PyTorch ecosystem and the SDK. We have a distributed data cache. Sorry, actually, I took that slide for you. I'll skip over. Transparent GPU checkpointing, support for Slurm and Flux. JAX runtime is mentioned, and Volcano and gang scheduling as well. And if you want to get involved, this is a link to the repo. Still making some modifications, but mostly done. And it runs this on a kind cluster. It's actually, I have some examples here of doing full RAG fine tuning, including the sentence encoder and the query encoder and the generator, doing llama 3.b2. But also this repo demo will actually focus on the retrieval optimization. I also give an example of fine tuning the hybrid retriever. And there's a lot of really great work that we're doing in the community to really make RAG and applied machine learning even better. So please come and join the community and have some fun.